Hi everyone, good afternoon. And now I'm excited to talk about our work, Losing Less, a loss for differentially private deep learning. This is a joint work with amazing Nicholas, and this is the work that we done when I was at the Vector Institute. But here I would like to acknowledge the feedback that I got on this paper from Sebastian, Franzi, Adam, Ahmad, Mohammed, that they are sitting over there. Okay, I know that you know that why should we care about the privacy, but let me motivate the problem here again. So we all know that machine learning models are often rely or trained on the data that we produce in our daily life. For example, financial data such as our transactions, or medical data such as our, for example, blood samples or so on. And this data clearly contains sensitive information about us, such as our HIV status, our habit, our lifestyle, and so on. And on the other hand, we know that machine learning models, they leak information about their training data that can risk the privacy of people who contributed, for example, to the training. For example, it has been demonstrated that an adversary who is only observing the output of the model, which is only the prediction here, can infer whether a particular data point was part of the training or not, which is the membership inference attack. Differential privacy is the gold standard for formalizing the privacy guarantees. An algorithm is said to be differentially private if it always produces effectively the same output on neighboring data set that differ by only one record. For example, in this slide, if you look at the top of the screen, we have a data set that contains a record of an individual, but if you look at the bottom data set, you see the data set without that specific record that corresponds to that individual. This is the definition of the neighboring data set that we consider here. More formally, a randomized algorithm, or here we are talking about the training algorithm, is differentially private if the probability that the learning algorithm A producing the solution S using the data set D is very close to the probability that the same algorithm A produces the solution S, the same solution, but here using the D prime as the input data set. And these two probabilities are very close in an interval that is bounded usually based on the parameters that we call it epsilon, the privacy budget, and of course the smaller epsilon that we have, the stronger privacy budget that we get. And if we can prove that this inequality holds for any pair of the D and D prime, then we can say that we have differential privacy guarantees. So now let's see that how can we train the model under the framework of the differential privacy. Typically, the way that we train the model is using the variant of the stochastic gradient descent, right? So in which we initialize the model parameters, and then at each training iteration, we sample a mini batch of the data point, we compute the average loss, and then we compute the average gradient of the loss with respect to the parameters, and then we update the model parameters using this aggregated gradient. Differentially private stochastic gradient descent, or DPSGD, train the model under the framework of the DP by introducing three main changes. The first one is that it computes the loss and the gradient on per example basis, because we want to allow isolation of the contribution of each training example to the output of the learning algorithm. The second change is that we clip the norms of the per example gradient, because we want to bound the sensitivity of the learning algorithm to each training example. And the last change is that adding the calibrated noise, which is coming, for example, from the Gaussian distribution to this average gradient. And then, okay, now using this noisy gradient, you can update your model and have the DP guarantees. If we look in more detail into the clipping and the noising, we see that, Okay, there is no priori on the per example gradient, which is GI here. So DPSGD artificially clip the gradient with the constant value, the L2 norms of the gradient with the constant value C using this formula. And then when you bond them using C, you can add the noise that is scaled by this constant value C and the noise multiplier, depending on your desired privacy budget that you want to get. Okay, there is no free lunch, right? We achieve the privacy guarantees, but we are losing the accuracy. In all the implementation of the deep learning with the DP that we are aware of, they all optimize the cross entropy, which works very well in the non-private setting. But let's see that does it work well in the private setting as well or not. So basically in this work, we challenge cross entropy as the de facto loss for the deep learning with DP. What we do, actually here it's an observation. So we observe that when you optimize the cross entropy loss function with DPSGD, it leads to exploding the logit value, which is like the values before applying the softmax, and the model weights. Why this is not desirable? Because both of these contribute to the gradient computation, right? So gradient is the function of these two. If they explode, gradient will explode as well, right? So we will end up with a large gradient magnitude. Then when you clip it, for example, with this constant value that is represented by the yellow color, you will lose lots of signal that is inside your gradient. And eventually you bias the learning, right? So here I'm showing you the cosine similarity between the aggregated clip gradient and the vanilla ones. You can see that some of them are not aligned with the trajectory of the stochastic gradient descent. So you bias the learning. And the other challenge is that when you use the DPSGD, you cannot just train the model forever. Because at each iteration, you are consuming some privacy budget. And so here, the slow training convergence of the cross entropy would negatively affect the performance of your DPSGD optimization. In this work, we try to address these challenges by tailoring the loss function to the specifics of the DPSGD. Our goal is we want to look for a loss function that converge faster with a smaller gradient norms, control better the sensitivity of the learning algorithm, increase the tolerance to the noise, and effectively learn both of the easy and hard examples. And we achieve this by proposing a novel loss function that is a combination of the sum square error between the logit values and the ground truth label, focal loss, which is the modification of the cross entropy to let the model focus more on the hard example, and the regularization penalty on the pre-activation, output of the layer before applying the activation. In the paper, we demonstrate analytically and experimentally that why this loss function makes sense. But here, because of the interest of the time, I just focus on two main observations. So it has been shown that a smoother loss function gives you better loss function for the training with DPSGD, because if you are in the sharp local minimum, when you inject the noise, you will introduce a lot of loss, and then you will drop the accuracy. And the most common one is based on the Lipschitz constants of the gradient of the loss function. And we drive the lemma that, okay, if you want to compute the smoothness constants of your loss function, you can just compute the maximum of the singular values. And here I show you that our loss function, which is the green one, is smoother than the cross entropy loss function, which is the red one, by tracking this maximum of the singular value over the training. And here, if you look at the green curves, you can see that our loss function can control the logit values, the model weights, thanks to the, for example, sum square error loss function that we define on the logit values and the penalty that we put on the pre-activations. And then eventually we get the smaller gradients, as you can see in green bars, and then we are better aligned with the trajectory of the SGD to get the better performance. And finally here, I would like to compare our loss function with the green one with the cross entropy in terms of the trade-off between the accuracy and privacy. In the y-axis, I'm showing the test accuracy. When you go from the bottom to top, the accuracy increases. And in the x-axis, you see the privacy budget epsilon. From left to right, it becomes looser. You can see that our loss function can improve the trade-off between the privacy and accuracy. This means that we shouldn't blindly just use loss function that works best in the non-private setting and hoping that, okay, they work for the private setting as well, right? We need to tailor our model loss function to the specifics of the DPSGD. Thank you so much.
Thanks a lot, Ali, for your presentation. We have some questions online. Two of them are actually quite similar, so I'll try to summarize. What is your stand on how much the choice of the loss function depends on the architecture, the domain, so for instance, vision domain or otherwise, and the type of data used to train the model?
Yeah, that's a great question. So in this work, we use the benchmark data set that we usually use in the DP literature. So a vision data set such as MNIS, fashion MNIS, and the most complex one is the Cypher10. But I think one of the promising future direction is that how can we design a loss function for large language model to be tailored to the DP training?
Yes, okay, thank you. Another question is about computational changes. So how computationally expensive is training with these new laws comparing to traditional laws? I guess that refers to convergence that you mentioned, but maybe something else?
Sure, yeah, that's a great question. So in terms of the computation, if you ignore the hyperparameter search, so we are the same level of the computation, we don't have anything extra. The extra things that we introduce our loss function, introduce a few more hyperparameters that we need to do hyperparameter search during the training to learn the value of that for the optimizing the privacy accuracy. Otherwise, it doesn't introduce any more computation.
Okay, thank you for the clarification. We actually have time for one more question. The loss computation relies on alpha, which in turn depends on the choice of threshold epoch. Can you elaborate on how you choose the value of the threshold epoch in your experiments for different data sets?
Oh, that's a good point. Actually, I hid this during the slide, but now I can say that. So we have the three loss functions that we are combining, and each of them has a hyperparameter. The way that we select those is that we want to learn at the beginning using the sum square error to just learn the easy example. Sum square error does the perfect job to do that. I mean, we show that empirically or analytically. And then we want to move to the focal loss that is designed to learn the hard example. We don't want this shift to be sudden, so we introduce the hyperparameters alpha depending on the current epoch and the threshold of the epoch, and then based on that and the sigmoid function, we smoothly go from sum square error to the focal loss, and we do hyperparameter search.
Okay, thank you so much. You can find Ali afterwards, so let's thank him again.
Thank you.